Hey, okay, we are live. Excellent. So, welcome to test 3 review. Maybe. There we go. Um, so again, just like last time, this is the slide that I project at the start of every single one of my tests, or at the start of every single one of my test reviews. Again, you will have the full lab block, 90 minutes, so bring something else to do when you are finished, because a lot of people do not take the full 90 minutes to take the test. Just like every other test, there are 15 multiple choice questions. Those are 2 points each. There's one lab based question, 1 point. Just kidding, 10 points for that one. And five free response questions. That's 10 points each there as well. Just like last time, you can bring one sheet of paper front and back, bring a calculator, and do, if you can, let me know ahead of time so that I'm not rushing around the day of the test trying to find one for you. I'll have one just ready for you. So the content on this test starts way back when we started talking about energy. There are three different types of energy that we've discussed so far. That's kinetic, gravitational potential, and elastic potential. Um, don't confuse elastic potential energy with elastic collisions. They don't necessarily mean the same thing. Specifically, elastic potential energy is just the energy that is stored in a compressed or stretched string or rubber band or bouncy ball if you're able to take a snapshot of it right as it hits the ground and compresses a little bit. Basically, anything that you can stretch or squeeze and it will pop back to its rest position if you let go, that can store elastic potential energy. Moving upward from that, gravitational potential energy is just uh, the energy that some object has when it is raised up to some height. Now, the interesting thing about I'll talk about that later. And kinetic energy is the energy that an object has just when it's moving. And that's it. So at any point in time, an object can have multiple types of this energy, of these energies, all at one moment. So for example, when I hurl this pen top over at Parker Wood, then, then when it's in the middle of the air, it has potential energy because the ground is down beneath it, and it has kinetic energy because it was moving. It did not have elastic spring energy. So when you go through either work problems where there's a change in energy or conservation of energy problems where there is not a change in energy, but it is transitioning between types, just be aware that an object can have multiple forms of these. And if you need to find the total energy of the object for any reason in joules, you're going to have to add these different types together. There's a ton of other types of energy. For example, Einstein's good old E equals mc squared. I'm not going to ask you anything about E equals mc squared, so don't worry about that. That's just the rest energy of anything. If you were able to convert your entire mass to energy, that's how you would do that. But we're not worrying about that yet. So just taking a little closer look at each of these different types, mass is the mass of the object in kilograms. Don't forget that kilograms is the base unit of mass, not grams. So if you are given a mass in grams, a lot of times in lab, whenever you calculate the mass or measure the mass using my scales up here, it'll give it to you in grams. You always need to be sure to convert that to kilograms. And that stands for the test as well. Uh, the velocity is in meters per second. So if you remember at the very start of the semester, I told you every single thing we do from August to December can be broken down to units of kilograms, meters, and seconds. It's just some combination of all of these things for the entire freaking fall semester. For gravitational potential energy, it's the same sort of deal. M is the mass of the object in kilograms. H is the vertical height above whatever line you designate as zero potential in meters. And G is the local acceleration due to gravity. On Earth, that's good old 9.81 meters per second squared that you've used over and over again. Um, One thing that I want to point out is this whole vertical height above zero potential. When you solve these problems, you get to tell me where the zero potential energy line is. A lot of times it's useful just to have it as the lowest position of the object, but it doesn't have to be. For example, if you've got a pendulum that's swinging down and back up above the ground, there's the ground. It's honestly your choice as to how you go about defining where zero potential is. For me, I like to say it's zero when the pendulum is at the bottom of its swing, because that means when I do my conservation of energy, um, equations, I can treat the potential as zero when it's at the bottom. Let's say I want to figure out how fast it's moving at the bottom. I can treat the potential as zero there. You got to be really careful if you do that to define h as simply the height above your zero potential line, not necessarily the height above the ground every time. If you want to keep things simpler, if that confuses you, don't worry about that. You can just treat the ground as zero. Call this one h1, call this one h2, and when it gets to the bottom, it will have both kinetic and potential energy, and that's perfectly fine. And the numbers will come out. I know they will from each and every one of you. Any questions about that weird concept? Okay. Then we've got elastic potential energy, where U elastic is 1/2 kx squared. Now this introduces the whole idea of the spring constant, K, in newtons per meter. All that K tells me is how many newtons of force I'm going to need to stretch or compress the spring 1 whole meter beyond its rest position. Uh, so that could be, well, that's not to say that I always have to compress or stretch it 1 meter. So for example, if it is a spring constant of 10 newton meters, or newtons per meter, sorry, 10 newtons per meter, any guesses as to how much force it will take to stretch it 1/2 meter? Yeah, 5 newtons. Done. Easy. Um, not too bad. And x is going to be the distance the spring is stretched. String is stretched, yeah, or compressed away from its rest position. So, as a reminder, every little piece of elastic, whatever, be it a spring or rubber band or whatever else, it has a natural rest position. If I take that and I stretch it, I'm only going to define x as the change in distance of its final little bit. It's not going to be the length of the entire spring. And the same deal if I compress it too. I'm not going to count x as as the length of that little compressed spring. It's just going to be the difference in the final position of that last part of it. That would look something like this. Then x will be from here to here. And by the way, all three of these types of energies have units of joules. And a joule is just a kilogram meters squared per second squared. So in the event that I ask you a question about energy and you cannot remember what the units are, just look at the units of what you have coming in here. For example, if you did a kinetic energy problem, I know the mass is in kilograms, my velocity is in meters per second, and I'm squaring it. So it simplifies down to kilogram meter squared per second squared. Same deal with gravitational potential energy. Mass is kilograms, g is meters per second squared, and h is meters. Oh, look at that. It simplifies down to kilogram meters squared per second squared. Nice. And same deal with elastic potential energy. I've got newtons per meter times meters squared. That simplifies down to a newton times a meter. But a newton times a meter, well, a newton from F equals ma is just a kilogram meter per second squared. So then it simplifies down to kilogram meter squared per second squared, and everything is beautiful. By the way, that whole equivalence of newtons times meters, that's why I can say that my work, which is force times distance times cosine theta, is also equal to a change in energy. There's my newton times meters. My change in energy is joules. The only way that equation can work is if the units are exactly the same, and by golly, they're exactly the same. How wonderful. But again, we'll get to work later on in this little PowerPoint. But I just wanted you to be aware of that. So if you end up writing kilogram meter squared per second squared, then I'm happy, thumbs up, you get a full credit for that question, even if you never write joules anywhere on that test. That is fine. Now, a lot of the problems that you're going to face are conservation of energy problems. Now, this is only when an object is able to freely move about under the influence of only a conservative force, meaning there are no non-conservative forces coming in and messing it up. Conservative forces include, like, yes, gravity and the normal force. Yeah, and yeah, that's pretty much it for this. So if you've got let's say like a roller coaster going around a loop, for example, you can use conservation of energy, assuming there's no friction on the track, because there never is in this class. Um, when you're faced with a conservation of energy problem, you can always set it up like this. Take the object's total energy before whatever event has happened. The object has fallen, the object has risen in the air, the object has, I don't know what else, it's rolled into a spring, something like that. You can take its total energy beforehand. That will include the object's kinetic energy. Does it have any before the event? If so, include that. The object's gravitational energy before the event, the object's elastic potential energy before the event. Set that equal to its total energy afterwards. So after it falls, or after it rises up, or after it pushes the spring in, or whatever it might be, the total energy will come to 1/2 mv squared plus mgh plus 1/2 kx squared. I mentioned before that it can have, when I started throwing things at Parker, that it can have multiple different types of energies at once, and that's true. You're probably not going to face a problem where an object has all three types of energy at once. Generally not. The only way that would work is if I somehow mounted a spring up on the wall and threw a block at it, and the block was in the middle of pushing the spring in and still moving. And I'm probably just not going to do that to you. Yes. Yeah. So with that, yeah, that's another good example. Yeah. If an elastic ball bounces on a table above where I defined gravitational potential energy of 0, and it compresses down on that table as it still moves, then yeah, it would still have all three types too. But I'm probably not going to ask you a question like that either. Um, but yeah, that's a good example. So a lot of times, before I even get started, just ask yourself, like for example, if there's not a single spring in the problem, or rubber band or anything like that, that's probably going to be 0. And then you don't have to worry about this part of it. Or if it stays at the exact same height through all of it, then both of these are probably going to be 0. You don't have to worry about this part of it. Um, so as you set your problem up, I think the most difficult part about physics is not so much that there's a whole bunch of equations. That's part of it, but that's manageable. You have a cheat sheet for that. It's setting up the problem to begin with and asking yourself, in this particular situation, what is applying here? And that can oftentimes be tricky. So conservation of energy problems can look very, very different depending on what's happening. Um, so hopefully tomorrow we'll get a bit of practice with that before test. Yeah. So I already wrote this down very briefly on that other page, but sometimes the total energy inside an object does change. And that's when some outside force comes in and messes with it, some outside non conservative force. So that could be me running up and pushing Parker over to get my pen top back. Or it could be friction slowing something down as it's sliding across the floor. Could be a whole bunch of different things. Yeah, friction slowing down two cars after they rear ended each other on the physics platform, like you all had to solve the other week. The work is just a change in energy in the object because of that outside force. It could be positive, and that's when energy is added to the object, or it could be negative, that's when energy is taken away. But regardless of if it's positive or negative, it'll equal the force acting on this object. D is the distance that it moves, not in full because of the force, only the distance it moves while the force is active. Um, So if I, again, run up and push Parker, then D is only going to be the distance that my hands physically push him. If once I let go, he continues to fall and roll across the floor, I'm not going to count that entire distance as D, just when my hand is in contact. Yeah. Oh, yeah, 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 that's a good question. Hmm. Yes, that's that's true. Yeah. It is right. So the way that so the question was about for the pre-post test that you all took about the elevator with the cable um, moving upward at a constant velocity. Is the tension greater than, less than, or the same as the force of gravity, or is it just moving up simply because the cable is getting shorter? Um, the answer is the forces are the same. Yeah. Yes, it's moving up because it initially began to move up. Yeah, it's moving up because at some point the tension had to be bigger than the force of gravity to accelerate it upward, and then the tension goes down a little bit until it's the same. The way I answered that question was to think of Newton's first law. An object in motion will stay in the exact same motion unless acted on by an outside force. So an elevator that's moving upward at a constant speed, um, that's what it would do if there were no forces present. The problem is we're on Earth, and there are always forces present because there's gravity. So the best we can do, rather than take away all the forces on the elevator, is to simulate that there are no forces on the elevator. And the only way to do that is to make the upward force equal to the downward force. So for a little bit, as it accelerated upward, tension was bigger, and then we simulated no forces on it by making the forces equal, and it continues to move up at a constant velocity like every object would. Um, yeah, right. Oh, yes. And the last little thing that I want to talk about on this slide is how delta E is just the change in total energy. That can be the final minus the initial. Anytime anything changes, it's just your final condition minus your initial condition. Always and forever. So whenever you see this little symbol right here, treat it as such. One thing to look out for, E is just the total energy of the object in joules. As I said earlier, it can have multiple different types of energy. So it would be my final kinetic plus my final potential, gravitational, plus my final elastic potential, minus the initial of all of these. Uh-oh, I'm running out of room. U, L, I, there we go. That is gorgeous. Just be aware of that. From here, you can distribute it however you want to. A lot of times, I like to move the kinetics to be next to each other, the gravitational potential energy to be next to each other, and the elastic energies to be next to each other. So it's K final minus K initial plus U final minus U initial plus the other U final minus the other U initial. That way. Some problems are going to ask you about the work, especially when we get to power, it will require you to find work over time. Depending on what you're given, you may have, you may only know about the energy and that change in the energy, or you might know a little bit about the force that was used and the distance there. Um, Basically, take what you know and find work one way or the other, but be a little bit flexible with it. The moment you see the word work, don't assume you have to jump to force times distance, because a lot of people do. Hey, I just talked about power. So as a reminder, a power output is just going to be work over time. Work over time. And it has units of watts. W. I've mentioned this before in class, but I'm going to say it again. These are not the same. Not the same W. Yeah, actually, yeah, that's really important. In mathematics textbooks, um, the joke was one is italicized, but in mathematics or science textbooks, in equations, whenever you see symbols, they're going to be italicized. Whenever you see units, they're going to be not italicized. Um, and I try to keep it that way as much as possible in my tests as well. Um, so the italicized is just a symbol. In this case, this symbol right here is work. So you all have already been able to handle the difference between mass and meter. Mass, you use little italic m, and it's in units of kilograms, and it's just a property that an object has. A meter is a unit of distance, which you'll probably use as italicized d or italicized r in a lot of these equations. Or if you're messing with a spring, italicized x. Yeah, yeah. So just be sure that you do not mix up work and watts, just like you wouldn't mix up mass and meter. Work is measured in joules because it's a change in energy. But that's about all you need to know about power. So a few ways this could crop up. I can either ask you if something was, let's say my car accelerated from 0 to 60 miles per hour in 4 seconds. What is the power of my engine? I could ask you that, and you have to tell me in watts. Um, or what's it? Find the change in energy. And in this case, it's only kinetic energy that's changing if I'm on a flat road. So 1/2 mv squared minus 0. Divide it by that time, those 4 seconds, and that'll get you the power. Or I could give you, just straight up give you the power and ask you how long a certain task will take um, based on the type of energy that's changing and solve for time that way. All right. Then we talked a little bit about Hooke's law. I already introduced elastic potential energy to you, but I thought I would write it up here again because it's still important. This is the force that a spring exerts when it is compressed or stretched. Um, so again, as soon as you see spring constant, a lot of people like to jump to this one immediately and say, screw you, this guy. Um, so just be aware of what you're given and what you need to solve for. If it looks like a conservation of energy deal, forget the force equation because force and energy are not the same thing. But if I ask you how many newtons it'll take to stretch a spring a certain distance, that's a good place to go. F equals negative kx. Again, k can only be positive. It's impossible for me to have to exert a negative amount of force to stretch a spring. This negative right here is only directional. If I pull a spring to the right, it will exert a force to the left. And that's all that that negative means. If you honestly just use F equals kx, then I'm not going to be upset because a lot of times we only ask about magnitudes of these things. So that's cool. Questions? I think I only told one class period this story, and I don't know why I didn't tell the others. But on my original slide, when I went through and talked about Hooke's Law, I used a picture of Captain Hook rather than actually getting a picture of Robert Hooke, which the law is named after. Reason is, nobody knows what Robert Hooke looks like. And the reason nobody knows what Robert Hooke looks like is because he and Isaac Newton were pretty much the biggest adversaries in the scientific world. So that when Isaac Newton became the head of, I can't remember, some sort of scientific society, he had all of Robert Hooke's portraits burned. And so that's why Captain Hook was on that slide. And I actually didn't know that at the time when I was first teaching this material. I was looking him up and I couldn't find any images, so I just grabbed Captain Hook and went on with my life. And then I learned that later. I just thought everyone's looking sad right now, so this is a baby sloth. You don't have to know that for the test, but look how small it is. It's just like it has to like reach all the way around to wrap itself around those two little fingers. Oh, and the image is from a website called Critter Babies. Oh, this is momentum. And the yells of anguish were all through the physics platform. Momentum, denoted by Lil P. Don't mix up Big P and Lil P. Big P is power, Lil P is momentum. They are two different things. But I guess they decided that M had been used for enough at this point. So momentum is P. It equals mass times velocity. Per usual, the object's mass is going to be only in kilograms. And the object's velocity will be in meters per second. Which means the unit is a kilogram meter per second. It doesn't get a fancy name. If you want to give it a fancy name and say that, one Pikachu is 1 kilogram meter per second, and then give me your answer in Pikachus, you haven't done anything wrong. The big deal with momentum is that the grand total momentum of a system is always going to be conserved no matter what, unless something comes in from outside the system and messes with it. As a reminder, a system is whatever you want it to be. Just close off some area. The total momentum inside that area is going to stay the same, no matter how many objects are in there, no matter how many times they run into each other. Total momentum is going to stay the same. Now, if something comes in and gives an object a kick from outside that system, that's where it'll change. And that's where you're dealing with impulse, which I'll talk about in just a second. Now, here it says, well, even as objects within the system collide with each other, these collisions between the objects can be a couple of different types. You could have elastic collisions and you can have inelastic collisions. The only difference is, well, A, do they stick together or not? And B, what else is conserved beyond momentum in these collisions? A couple of people are still furiously scribbling, so I'm just going to hang tight for a couple of seconds while they do that. Everyone have a good weekend? Just anything that's not in the system. So it could be friction is a good example because that'll take away momentum of an object. Yeah, if two cars ran into each other and then friction acted on them, yeah. But if you look immediately before and immediately after the collision, before friction has really had a time to interact with it, then momentum's going to be conserved of those two cars. Um, yeah, that's mostly what we're going to be looking at. It depends on how you define your system, honestly. If you were just focused on only one single car, and the momentum of that car is the momentum of your system, and that is it, its momentum will change because of the collision. Then you're looking at an impulse problem. But if you want to zoom out a little bit and say these two cars both have momentums, if I add the momentum of the cars together, um, then that's the grand total momentum of the system. And even if they collide, that's not going to change. So it's a little bit weird, but you can define a system to be as big or small as you want to. But once you've defined it, that's that. Most of the collision problems that we're going to do will just be conservation of momentum problems, would be the easiest way of solving it. Sorry, Parker, did you have a... Um, nah, I'm going to keep it pretty simple. Basically, the your WebAssign problems I try to make harder than your test problems on purpose because you have more time, more tries, and more resources available. Um, so if there's a simplification that's done in the WebAssigns, odds are I'm not going to make it more complicated when you get to the test. Yeah. No, because I didn't have time to get around to that. But I have made a note to myself to add it for next year's. Yeah, because I'm excited about that. If there's a coefficient of restitution, it tells you how elastic a collision is. What, like a range from... Yeah, like when you mess with it on the simulation, what range from inelastic to elastic is it? All right. These are not the only types of collisions that exist in the universe. In fact, most collisions are going to be somewhere between perfectly elastic and perfectly inelastic. Um, but for the purposes of this class, just as you're being introduced to this idea of momentum and collisions, I'm just going to look at these two extreme examples and leave it at that for now. In a perfectly elastic collision, the objects just bounce off of one another and go in different directions. So that will have both momentum and kinetic energy conserved. If it's perfectly inelastic, then you lose a whole mess of kinetic energy, um, as much as you possibly can in that collision if it's perfectly inelastic. But momentum is still conserved. And the two objects stick together and travel off with one single velocity afterwards. Once again, most collisions, you're going to get a little bit of a bounce in it, and you're going to lose some energy to heat, um, but not all the energy that you could possibly lose as a result. But we're just looking at these two extreme examples right here. Yes, yeah. You had two objects and they stick together for a little bit, then yeah, that collision, if I'm asking you for the velocity right after it, then you can treat it as perfectly inelastic. If they later bounce off of one another, then it's technically considered an inelastic collision, but not perfectly inelastic. I forgot I was tethered to this computer, and I just like strangled myself as I walked away. Oh, that was uncomfortable. Okay. Any other questions on this mess? A good resource to use to practice some? Yeah. The force diagram? Yeah. Is there anything quite like that? Not that I know of. That was called the FBD Interactive. I don't know if they've got one like that for energy. I do know a lot of PhET simulations are really good. I've introduced you to some of them, but not all of them. Um, a lot of times that's a good place to look because they will give you actual values as well. So if you have the incoming numbers, you can pause the simulation, calculate what it'll be after the collision, and then run the simulation, and that'll give you an answer. Um, Yes, I know they've got a good collision one that I... No, I think I had you use... But I think you only scratched the surface of it. There's a lot more it can do than I made you do in that activity because we were just getting introduced to it. Um, so yeah, I highly recommend that, PHET. Beyond that, there's last year's test. You can see the momentum problems that I gave there, as well as a step-by-step walkthrough. Tomorrow, you're going to go through a series of stations practicing the types of problems that you want to practice. I've got the solutions already printed off, and I'll have that up on Canvas as well, if that helps. All right. So for elastic collisions, when I say momentum is conserved, here's what I mean. The total momentum of the system is just going to be the sum of the momenta of each individual object. So before the collision, that's going to be everything on the left side of the equation. The grand total momentum of the system before the collision is over here. And the grand total momentum after the collision is going to be over on the right side of the equation. And honestly, I could say the same thing for the kinetic energy equations. Before the collision is on the left side of the equation, after the collision is on the right side of the equation. Now, here's a biggie. Don't forget, if you've got two objects going in opposite directions, momentum is a vector, so it needs a negative if one's going right and one is going left. Do not forget the negative values of velocity there. For kinetic energy, which is a scalar, negatives don't matter, especially since negative 2 squared is just 4, and 2 squared is 4. So for kinetic energy, don't worry too much about negatives. But for momentum, that is a vector, the velocity is not squared, you do have to worry about negatives there. Yes, sir. Yes, the bottom one is the conservation of kinetic energy in an elastic collision. Top one is the conservation of momentum. Momentum is mass times velocity. Kinetic energy is 1/2 mass times velocity squared. Right. So let's say I've got two football players running at each other. Or hopping toward each other. Or sitting and moving toward each other. And they're about to collide. Let's call this person number 1. Let's call this person number 2. If this is the setup for my problem, notice that number 1's moving to the right, number 2 is moving to the left. V2 had better be negative, or else I'm going to get an incorrect answer. Essentially, if I don't include the negative for V2, then I would solve the problem as if the two football players were running in the same direction, and one just hit the other one from behind. Then that's the answer that I would get out of that. But they're not running in the same direction. They're sprinting toward each other. So, yeah. So don't forget the negatives in that sense. Right. For the bottom equation with kinetic energy, V is squared. So it doesn't matter if V is negative or positive. It comes out the same. Nice. Any other questions or thoughts? Cool. For inelastic collisions, it's a little bit easier. Again, perfectly inelastic collisions is how I should have labeled this, not just inelastic. Perfectly inelastic. For these collisions, kinetic energy is not conserved, so I can't have that bottom equation of the 1/2 mv squared before and after equaling each other. For these, kinetic energy is lost, so all it is momentum. Once again, do not forget to include positive or negative for each of these velocities, depending on the direction that it's moving before or after the collision. And so far, all we've talked about has been one-dimensional collisions. This is assuming they're both on the same straight line running backwards and forwards toward each other. That's not always the case either. So be prepared for 2D collisions if it comes up in class. The nice thing about perfectly inelastic collisions is that the final velocity is exactly the same for both m1 and m2. That's why I can just factor out an m1 and m2, pull that out to the side, and that makes it really easy to solve for the velocity after the collision. Inelastic collisions make my students so excited they start show choir dancing in the middle of the review session. All right. Now, just a reminder of where we've been. There's kind of a pattern as to how I'm going about this. I talked about energy and the energy contained in objects. A lot of times it's conserved. Unless a force comes in and messes it up, now you're dealing with work and power. Then we've got momentum. For a lot of collisions, momentum is conserved unless an outside force comes in and pushes things around. Then you're dealing with impulse. So impulse is just a change in an object's momentum because of that outside external force. Change in momentum equals force times change in time. And remember, every time you see a Greek letter delta, that's final minus initial. So I could rewrite it as mass times my final velocity minus my initial velocity equals force times my final time minus my initial time. Typically speaking, we say that time is 0 when the interaction begins, so you're usually not going to have to worry about that. Typically. But it's just the amount of time the force is active, which I feel like I should probably write down. Delta T is the amount of time the force is active. Just like D in the work equation is just the distance that the force is active. So once again, if I go and tackle Parker for my pen top that he still hasn't given back to me, then delta T is just going to be, no, I don't really need it. It's a gross pen top. You can keep it. Delta T is just going to be the amount of time that I'm actually in contact with him. Again, if I push him and let go and he continues to fall, I'm not going to count that time that he's falling once my hands have let go. It's just from the point of when contact is made to when contact is released. That's what delta T is. So a lot of times for these impulse problems, delta T is going to be pretty small. For example, if I run into that cinder block wall right there, then it's going to stop me pretty quickly. And delta T is going to be probably less than a second. If I run over to the wall, to give you an example, but instead I forget I've got my headphones on and it chokes me out, then odds are I'm not going to let it continue to do that for multiple seconds, unless I'm really desperate to get over there. Oh yeah, just real quick, make sure that we're still actually recording by looking at the other screen. Hey, we are still recording. Very good news. Okay. You may find some collisions are in 2 dimensions. Momentum, like I said earlier, is a vector. Vectors can have both x and y components. So, if you encounter a problem where 2 things are moving in different directions, you're just going to treat this like you would any other vector problem with more than 1 dimension. And that's going to be this. You're going to break every object's momentum into x and y components. can talk so much faster than I can write. 2, you are going to add all the x's and add all the y's separately from all the different objects. Once you've done that, you've found the momentum in the x direction and you found the momentum in the y direction before the collision. Because momentum is conserved and it is a vector, that means its x component is conserved and its y component is conserved. So once you've done that, a lot of times, I'm probably only going to give you two-dimensional vectors, two-dimensional collisions that are inelastic because it's a bit easier. From there, to find the final velocity, well, you know the final momentum of these two objects stuck together in the x direction. You know the final momentum of the two objects stuck together in the y direction. To get the ultimate final momentum, you can just Pythagorean theorem it. And you've got the full momentum. Once you've got the full momentum, don't forget, a lot of times I'll ask about the velocity, not the momentum at the end. So it'll equal the total mass times the velocity. Divide by mass, you got your velocity. Good old Pythag. So I gave you some questions like this on the WebAssign. A couple of them involved a couple of cars at an intersection. I did a problem just like this. In fact, I'm going to go ahead and write up here. To look on Canvas for the football problem. We did it in class. Most class periods at least got a start on it. Most weren't able to finish it. So I finished it and put it up on Canvas. I think it's under module 5. So that'll be a pretty good example to look at before the test, most likely. All right, so I'm going to close it off real fast with just a couple of little conceptual questions for you people, and that'll be about it for us on this upcoming test. Block 1 is dropped from a height of 5 meters. Block 2 is allowed to slide down a frictionless ramp from the exact same height of 5 meters. Which one is going to take less time to arrive at the bottom? Say same amount. Oh, that's a really good thought. Oh, and I'm really glad you said that, actually. You said the x and y components don't affect each other. The difference is the ramp is not perfectly vertical, so the normal force is going to have x and y components. So because of the normal force, block 1 is going to take less time to get to the bottom. And I mean, you can test that out too. Take a couple of balls and drop one and put the other one down a ramp and see which one arrives sooner. Oh yeah, no, they're not being dropped on the same ramp. One is just dropped and one is allowed to slide down a ramp. How about this one? Which one will have a faster speed at the instant it reaches the bottom? Yeah, if the ramp is frictionless and you do conservation of energy, which would just be, there's no spring, so that's just going to be K initial plus U initial equals K final plus U final. Well, K initial is 0. They drop from rest. U final is 0 because it gets to the bottom. So mgh initial equals 1/2 mv final squared. Notice that I gotta stay consistent. Notice that its mass doesn't matter, and the path it takes doesn't matter. If it falls over the same height, then it has the same speed at the bottom. That's why I had you all do the ramp and pendulum experiment to show that it's the same velocity if the same drop in height happens. Yeah. Cool. Cool, cool, cool. It's just that block 2 will take longer to build up that speed. But it will have the same speed at the bottom. Any questions about any of this? Heck no. That was a big old resounding no. Everyone dove for their backpacks. So, with that in mind, you all have a fantastic afternoon, evening, and I'm going to stop this here broadcast.